Okay, day 4. Now let's first start with linear algebra. I felt like that didn't go too well last time, so I want to do a little recap. There were some words, can be some bit of confusing, but actually aren't. So first, a little recap. Space versus set. These words is used a lot interchangeably. So a set can be a set of anything. It's like a set of cats or a set of fish or a set of cats and fish. It's just a collection of something, and that something doesn't have duplicates, and it may have some order, and that order is just, like I said, set of cats and fish. That's the rule here. There's nothing special. But a space is something with more structure, like a vector space. There are other types of spaces. You just so used to the word space, you just think about vector space, but there are other types of spaces. There's topological spaces, for example, but in this case, we're keeping it at vector spaces. So why do vector spaces have structure, right, compared to just a set, for example? So a vector space, for example, the reason why it has structure is that a vector space, it's required that we can add vectors and we can scale them by scalar multiplication, right? That is what we want. And what is certainly required are those 10 rules. And those 10 rules, we're not going to go through them again. Most of them is about adding, then the rest is about scaling, and then you have some weird ones like that 1u. I think that one actually belongs a bit to the scaling, is equal to u. And of course, you also have that if you scale or add the vector, those vectors has to be still in that vector space. So for example, or still in that set, you could say, because as we will see later, we can abstract these ideas, right? We can have a set of anything, but if that set has this structure that a vector space has, we can treat them as a vector space. That is, I think that's one of the core things in linear algebra. I don't know yet because I haven't done a lot of linear algebra, but I think that is maybe the conclusion that we are going to arrive at. So for example, if we had polynomials, let's say we have polynomials of less than, so we have some polynomials and it's less than some degree of n. So let's say a polynomial of 2 degrees. So p of t is equal to, let's say, a1 t squared plus some t. And of course, I could have another polynomial, same way. I can add that together with the one I wrote there. And that should be fine as well. Even these two are different, so can I do that? And of course, I can scale a polynomial. T here could be 0, that could be the 0 vector, etc. So this is a polynomial. It's not our geometric interpretation of a vector that we are used to, but still, it behaves as the vector space, right? So I think all the properties of a vector space should apply. I think that's the idea we're going to arrive at the more we do this. Okay. Example. Let's say functions, for example. So I have this example from the book. So let V be the set of all real valued functions. So V here is the set of all real valued functions. And it's defined on some domain because, of course, the function has to be defined of some domain. What I'm trying to say is that it's defined on some set D, and that this set is, you can just imagine it as the real line, right? Because a function has to take in some value. So the function is a real value, but it, of course, has to be defined on some domain, right? So T, in this case, is in the domain of D here. Okay, so let's say we wanted to add, so we have, for example, f of t. I could, of course, add that with g of t. There's no problem in doing that, right? Usually you write this actually as, it's a little bit weird, but you write f plus g of t. That is no problem. I could, of course, also scale to f of t, right? And if there is some t value, that f of t is 0 for all t, of course we have that 0 vector property then. And of course the negative of f is just minus f. So you see here, these are functions, but they can be treated. This set v here, can actually be treated as a vector space, even though it's just functions. So that's pretty cool. Okay, that was just a little recap from what I did last time. Okay, subspaces. So now let's get back to the idea of subspaces. So subspaces, they're actually pretty similar to a subset, right? It's just it's like the subset, you have some domain and you take a chunk of that domain. It's like we have a space of vectors, and a subspace is not all of those vectors, it's some portion of those vectors. But in order to be a subspace, again, since it's a space, it has to follow some rules, right? So those were the rules I mentioned last time. Of course, if I added two vectors, let's say I added two vectors in this space, if I added two vectors in this space, though the resulting vector from those two added, the resulting vector should be under the closed set of this subspace, right? What I'm trying to say is that was a bad one, but like I drew last time, like this. If I added any arbitrary vectors here, like this, they have to, no matter what, the resulting vector, which is this guy, has to also be in that space. That's it. Also, of course, since we need a starting point, they also have to go through, of course, 0. So we have the 0 vector. And the third and last property, of course, is that if I scale, that scaling also, the same rule applies to scaling like we had with addition. So if I scale this vector instead, like this, the resulting vector, which is this whole vector here, that should also be in the space, which it isn't, so this isn't a valid subspace. So this isn't a subspace, right? Okay, cool. Very good. Okay, let's see. I wrote some example here. What was the example? If P was the set of all polynomials with real coefficients, with operations in P defined as for functions. P was a set of polynomials with real coefficients in P defined as for functions. Then P is a subspace of... Let's see. So I wrote to myself, if P was the set of all polynomials with real coefficients, so the coefficients are real, with operations in P defined as a function. Oh, okay. Yeah. Then P is a subspace of all polynomials. Of course. Yeah. As we looked earlier, right, if P, the set of all polynomials, right, if I have some P here, which is a set of all polynomials, and they have real coefficients, and they have same operations as for functions, then of course P, as we saw earlier, the polynomials, is of course a vector space, or you could even say it's a subspace of course, because this polynomials are of course functions. And if they apply to all of these rules, which they do, because you can add polynomials, you can scale polynomials, and if they go through 0, we're fine, which means that P is a subspace of functions. And then if we again restrict to some polynomial, let's say P of n, that still has the same properties, that is also a subspace. That's one below there again, right? So you also have that subspace as well. Okay, that's what I wanted to speak about. Okay, We also have, I did a lot of examples here. I don't know if I need it. We also have, yeah, I can do this one as well. We also have the discrete time signals again. So discrete time signals, they are just data points in time, right? And the last one we had was that y of k. So we had some set, which was the discrete time signal set S. And in S, there was sequences. There were these types of sequences in S. And these types of sequences represented discrete time signals. And these sequences, they are doubly infinite. That is what we had. And we found out y minus 1, y of 0, y of 1, and etc. And we found out that this is a vector space. We did some adding of another sequence because we can add another sequence like this. This was more of a general. You could scale it, etc. It applied to all the rules. And now we could check if, let's say this was discrete time signals, but let's say instead that we had finite supported signals, which means that we are going to have finite of non-zero values. That is what I want. So another vector space, let's call it S again, but F for finite. And there is here finite non-zero values. This can be, this guy here can be anything. This can be only 0. This can be only non-zero numbers. This can be 0 and non-zero numbers, etc. It doesn't matter. But this guy below here, he has an infinite amount of digits or numbers here, but digits, numbers is better. But there's a finite amount of non-zero numbers. That's the difference from this guy. So let's say y minus 2, I could just, to make this clear, just 3 to maybe 20, for example. And maybe these are the only, maybe the rest is just 0, for example. And these are the only, so there's finite non-zero numbers then. Okay? Since there's a finite non-zero numbers, of course, there can only be 0, 2, which means that we can define the 0 vector like we would do earlier. I wrote vector that doesn't quite make sense, but it's all right. But we can also, I do this instead. That makes no sense. Instead, to define what we would have as a non-zero number, we could do this. So this is only 0 here in this guy. This sequence only has 0. And this can be, of course, in this guy. And of course, we can, like earlier, we can add and still be in the sequence. And of course, we can scale and still be in the sequence. Of course, this finite sequence is, of course, a subspace of this discrete time signal space, right? Okay, that's what I want to say. Those signals are just weird. Feels like so weird. I don't know. It's all right. Okay. Yeah, let's see. Now we can look at some better examples. So this one is a more fun one, more of one I like. So actually, the vector space. So not the vector space. Yeah. The vectors, a space, or no, you can say it like this. R of 2 is actually not a subspace of R of 3. That's pretty cool. It's not even a subset. Why is that? And that's, of course, if it's not even a subset, of course, not a space. So here is how you imagine that. Because as most of you would have done or thought, is that, of course, I could have this and I could have this, right? If I have a vector here, I could have the same vector there. So why isn't that true? The thing is, these are actually two different things, right? If I write this vector in 3 dimensions, it looks like 2, 2, and of course 0. So this is 2, 2, and 0, and this is, for example, 2 and 2. Now, the guy on the left here is a 3-dimensional vector. Even though it's 0 there, he's still a 3-dimensional vector. And this guy is a 2-dimensional object. Of course, it's not a subset. These are not the same thing. So, of course, since it's a subset, of course, it's not a subspace as well, right? So, you can see here instantly, if instead we created, let's say, I created this vector space here. So let's say I had T, S, and 0, and these T and S were a part of the reals. You could see that this plane here, this is a subspace of the vector space in R of 3. You can see that pretty clearly, because now we are actually just confined to this plane. And R of 3 has all of this as well. And we also would go through 0, since T and S can be reals. We'll go through 0. And here again, if I add, I will still always be in that plane. The plane is infinitely large. So if I add or scale in a vector, that is still under the under the closed set of that plane, right? So of course we are now a subspace. I mean, of course. So that works. Okay, and now you can actually see if you think of a plane, of course there's another way, because if we span a plane, this will be true as well. So we can look more into that. But first, if you want to look at a subspace spanned by a set, we have to look at an old definition called linear combination. So what is linear combination? Linear combination is just the let's say I have some vector, and it's just all the combinations I can create by the scaling and some other vector. So I have v1 here, and I should have x of I. I should have x1, then I have v1 like that, x2, v2 like that, x3, and then v3 like that, and all the way up to some n, so x of n, then v of n. You see, this is a linear combination of multiple vectors, right? Forming what u is here. Okay. Yes, and the amount of vectors we have can, of course, be different than what you call it, than, of course, in the space that they live in. For example, I could have 10 vectors here, which is n, so let's say that n was equal to 10, but all of these vectors, let's say v of I, all of these could be in, let's say they are in R of 2. There's no problem with that. So those two things are not the same, right? Okay, yes. So an example of that is, let's say I wanted to have, for example, you could do 2, and I could have 1 and 0, and I could do plus 3 and minus 2 and minus 2, which will give me the vector, as you see, of course, 2, 0, plus, I can just keep 3 there, and I just do that, minus 6, minus 6, like that. So this is a completely new vectors you see here as well. Of course, I could add those two together just to make things even more clear, minus 4 and minus 6. Right. So that's a new vector, and it's formed from the linear combination of others, right? Okay. Yes. Yeah. Okay, let's say if we wanted to check if two vectors, my notes today were completely stupid. Let's say I want to check if two vectors can be scaled and add into new specific where the scaling is unknown. Why do I need that? That makes no sense. Yeah, just skip that. Okay, so the idea here is that you can see we're starting to see what span is. That will become clear now. So you're already familiar with span, right? If I have 1 and 0, and then I have 0 and 1, then I could say that any linear combination of these two vectors span the two-dimensional plane, right? Because if I had, let's say, some constant here, C1 and C2, I could span the whole of R2, right? This means that if this guy, let's say this guy is called vector 1 and this guy is called vector 2, this means that the span of V1, comma V2 here in this case is equal to R of 2, like that. Very good. Okay. Great, then we have that, and actually this is what, if that span, yeah, that will come later, but these two spans are actually what is called bases. Yeah, they form the basis for that whole, vector space there. Okay, that's all right. Now let's go to a more complicated example. So we have example 11, given that we have V1 and V2. Let's say we have V1 and V2, and they're in a vector space V. They're in a vector space V, like that. Now let H be equal to the span of V1 and then V2. This is not the same V1 as V2's here. These are just arbitrary V1 and V2. Now we want to show that H is a subspace of V, right? Okay? So we can do that pretty easily. So what I can do is that I could say, let's say, yeah, so of course I could, if I had some S of I and some T of I that were in the reals, I could say that S1, if S1, let's say S1 was 0, so a 0, V1 plus 0, V2 is the 0 vector. Awesome, that's the first one out of the 3. Now we can do addition. So let's say I had some vector u, which was equal to S1, V1 plus S2, V2. And then I had the vector v, not v, w, that would be better, w, which is equal to S1, v, no, yeah, shouldn't that be alright? Yeah, that should be. No, maybe I'll do, oh, no, that was foolish of me, of course, that was wasn't that foolish? No, I can do that, yeah, that's what I want to do that. So I can do T1, V1 plus T2, V2, like that, awesome. Then, of course, I can test that linear combination idea, so I could say U plus V, and of course I can take out the constants, so I have S1 plus T1, of course, V1 there, and then I have S2 plus T2 like that, V2. Perfect. Here you see, these are just constants. Of course, I can scale those. That's no problem. So addition here works. This is just any number. And both of these S1 and are in the reals. Of course, if I add them, that's still in the reals, so that's still all right. Okay, and you could also see that if I did the scaling, this would actually work. And this is a very generalized example. You can see I didn't use any numbers, which means the first theorem that we actually have. This gives us the theorem that actually, if we have two vectors in a vector space V, then the span of those two vectors is a subspace, right? And we saw how that made sense from the 3 to the 2-dimensional case when you had two vectors, of course, they span a plane. Of course, the plane is, of course, if beforehand what we had was a vector space, right? Those two vectors, of course, they are going to be a subspace of that vector space, right? Because they would span a plane that will go through the origin, right? Okay? Because again, you have to use vectors from, okay, well, I can be a little bit more clear. Let's say I have the three-dimensional case, right? Like this. If I pick any two vectors, the vectors has to go through the 0, right? So any two vectors, regardless of who I pick, they have to go through the origin, because we know that this is a vector space. That's one of the things we have required, right? So it's a vector space, okay? And now, since this is a vector space, that 0 property, or now since we have that 0 property, the first property we need is okay, right? And this will of course span, I should do another color, and this will of course span a plane like this, right? And that plane is of course infinite. So any combination, either scaling or adding, would work, right? So this is like the generalized idea of that span. So if we have a span of these two vectors, and those two vectors come from a vector space, that span is a subspace of that vector space. That's what it means, right? So that's the first theorem. Okay, now I just wrote example 12 to myself. So we need to go and check what example 12 is. Let's see. Linear algebra and its applications. Example 11. There's what here is the example 12. So let's us not see the solution. Okay, so let H be the set of all vectors. Okay, so H is the set of all vectors of the form. Then write it like I did last time. So H is this set of vectors of the form A minus, my 3 was annoying, 3B. And then it is B minus A. Then it is A. And then it is B, like that. Okay? And where A and B are arbitrary scalars, so we can just say that they are in R. So A and B are reals. Okay? Okay, so now what we would, that is blah blah blah, A and B in R, and show that H is a subspace of R4. Okay. So we want now to show that this set right here, this is a subspace of R4, and what we can do is use that theorem. So the only thing we need to do is create those two vectors, and they should live in R4. Okay. You can be a little bit clever now, because if you are, you can see that we can set A outside, right? A outside, and A here, that's just 1, that's just minus 1, that's just 1 again, and 0. You can call this V1. Then we have V2, which is equal to B, and the first one is minus 3. The second one is 1, 0, and then 1. And now you can see that since V1 and V2 are in R4 and they span, of course, the span of V1 and V2 is equal to H. That means that by theorem 1, H is a subspace. So that's it. Okay, perfect. Now we are going to do some tasks. Let's see here. What I can do is I had this visual. Yeah, that was very nice. I like that visual marker there. Let's see. Okay, so the first task I wrote. It's just I do task 5 again. I didn't do that too well, I thought. So let's do task 5. Okay, so task 5 here. I can zoom in. Yeah, that was better. Okay, task 5. All polynomials of the form P of t, and of course I need, I have been I've been messing around. Okay, chill. In exercises 5 to 8, determine if the given set is a subspace of p of n, so all the polynomials, for an appropriate value of n, or all but any polynomial. Okay? Justify your answer. Okay? So p of n. So we want to check if it's a subspace. We already know that p of n is a vector space. I want to check if the one we have here is a subspace. Okay? And in task 5, what we have is just equal to a times t squared, where a is in R, of course. So a is then in R. Okay? So you have to check if this is a subspace. Okay. Yeah, we can do that. There are multiple ways of doing that. The 0 here is no problem since a is of R. Of course, since a of R, a can be equal to 0. And then we have the 0 vector. You can see that we can add and scale here without any problems, but there's a better way of doing this. We can use that theorem again. You can see that the span here, of course, of t squared, so you can see that that of course, oh my god, if we let h is equal to the span of t squared, because that constant in front doesn't matter, it's span of t squared, it will be the same as we had with the vector. How can I argue this guy? Oh, it's easy, come on. The span of t squared, the space that this is spanning, of course, it will be t squared and all the possible reals in front. That means, of course, that this is a subspace. Yeah, same as we had earlier, right? Because this t squared that we had from earlier, that is also a part of the polynomials, which is a vector space. So that means that the spanning of t squared is a subspace. Yes. God damn, my brain is stupid today, but that's all right. Okay. The next 8 is that we're going to do the same thing here. And now we have all polynomials in p of n such that p of 0 is equal to 0. So we have all the polynomials in Pn. Yeah, that means that we have all the possible, that should be, we don't even need to do many much, because this is all the polynomials and they all satisfy that 0 requirement. And we already know that all the polynomials can be added and scaled, so you don't need to make that too complicated. Okay. All right, let's go to some different tasks. 9, of course. Let H be the set of all vectors of the form S3, S2S. Find a vector V in R3 such that span, why does this show the subspace? Yeah, so we can use by that theorem 1, of course, we can just move S outside, just like that example. This is not something to waste our time on. Okay, now let's do the last 2 tasks. Okay, I should use that one, it was pretty good. Okay, in exercises 15 to 18, let W be the set of all vectors of the form shown, where A, B, and C represent arbitrary real numbers. In each case, either find a set S of vectors that spans W, or give an example to show that W is not a vector space. We can do this pretty instantly on the first one, because no matter which number I put in front here, this shouldn't work. And you can see why. I can move A, so I can move some combination here, not in front there, that's stupid of me. Okay, start again. This guy right here, I can express him in terms of A and B. I can create 2 vectors, but regardless of those 2 vectors, I can't get rid of 4 here. Okay, let me write it. God damn, okay. Let's see, okay. So I have 3, A, I have 4, and I have A minus 5B, like that. Okay? So you see here, I can try and express this. Let's say if I had V1 here, and I put A in front, then I would have 3 and 0 and 1, like that. Then I'll have V2 like that. And then, of course, I would have 0, 0, and minus 5. And now you can see we can't satisfy 4. And that is not one part of the option, because this is how W is written. So W is written as like this, where A, B are reals, right? That's our set. So we don't have any option to add 4 here. We can just change A and B. That's all we can do. So, of course, that's not a possibility. We can't satisfy that condition. Okay. Now 17. 17 is a lot better. So let's do 17. Then we'll have A minus B. We have B minus C. We have C minus A. And we have B. Like that. So we have a set which is like this, where A, B, C are all reals, like that. Okay, that was pretty stupid. Nice. Okay, so let's see now. I can create a vector v1, and v1 is equal to A. That's just 1, 0, minus 1, 0. v2 is equal to v2 is equal to B, so of course, minus 1, 1, 0, and 1. And then v3 is of course equal to not A, you moron, C. And then we have C, that's just 0, minus 1, 1, and 0. And now we actually manage to create this vector here, which means that the 3 of these vectors, they actually span W, which means that these 3 vectors actually creates a subspace. So the span of v1, v2, v3 is a subspace. Okay, cool. Pretty good. Oof. My brain is hurting here. Okay, yes. Then we're going to do some statistics, so that's even better. Okay, astrophysics then. Okay, we're going to continue where we were last time. So we did some Gaussian statistics, but now we're going to do multi-dimensional distributions. So it's better to view from an example. So instead of just asking the probability for height of women in Norway, we ask what is the probability that a woman have a, let's say she have a height. It's a probability that she have a height between 170, 175, and, not or, but and, an IQ. That was a great Q. An IQ between 120 and 130. And as well a blood pressure. So this can go in, of course, in centimeters. And blood pressure between 70 and 79. That is the question we ask now. This goes in millimeters. I don't know what that means, but that's just it. Okay. So that's the probability that that's the probability that we're looking for. The combination of all of these together, right? Okay. So in order, and of course with the IQ we have a mean. So let's say here we have a mean of 100 and a standard deviation of 16. And here we have the mean of 80 and a standard deviation of 10. So that's a lot. Okay. Okay, so in order to answer this question, we need to know that these probabilities are multiplicative. And that actually just means independence. In order to multiply all of these probabilities and combine them, you need independence. So we can assume that they are independent, but they are not completely independent for some reason. But a good assumption is that these are independent. So what is independence then? Okay, independence is that the probability of some random variable, let's say the probability of some event A happening, wasn't affected by B. That's what I'm written here. So for example, me chewing this pen, let's say, was it my birthday yesterday, or did the seagull fly past my window? That doesn't affect me doing this. Maybe birthday because I get older. I don't know. But is it night or day? Whatever. Some event that doesn't affect. Was the car that drew past here that event B? Was it blue? It doesn't matter if I drew this pen, right? Of course. And this, of course, means that the probability of some information of another event that didn't affect is just still the probability of A, right? This, of course, goes both ways. So we have this as well. Also, why we want multiplicative, you can see now, because from the independence formula, actually, the probability of some event A given B, like I said, was P of A, but that is also equal to P of A and B restricted to the domain of B. Now, you could just move this guy here, and you could have that if we have two events, A and B, and they're independent, P of A multiplied by P of B is just what it is. So if they're independent, we can ask what's the probability of two separate events, and it's just multiplication, which is what we want. So actually, in our case, the question that we are asking is actually the probability of age, IQ, and blood pressure is just the integral I had from, let's say the integral was from 170 to 175, wasn't it? Yeah. And that is DH, and we multiply that by IQ, which was 120 to 130. So you get the DIQ. That seems pretty stupid. And then we have blood pressure, which was from 70 and 79. The blood pressure, and of course, we need to multiply by the actual probabilities, or the cumulative probability density function. So this is just P of H, then we have, I need to move this because this was not a lot of space there. This is just P of H multiplied, and then P of IQ in terms of IQ multiplied, and I can just write here, it seems stupid, but who cares, of P. So that's our question. That's the combination of all of them together, like. So that's what we want. Okay, yes. Now we can go one step further. Now we know what multiple event, what's the probability of them, and if they are independent. So the next step now is what is called the central limit theorem. Now, before starting central limit theorem, we can look at the law of large numbers, which is pretty intuitive. So given that I have some sample, so I have some mean like we had, and this is just equal to 1 over n, and the sum x of I, and then n, right? We have some sample mean here, right? And let's say it was coin toss, for example, it could be height, etc. Doesn't matter. And if we now let n here go towards infinity, what will happen is that sample mean will actually approach the true population mean, which makes sense. I can throw a coin, I can get 4 heads in a row, right? Or 4 tails in a row, but that doesn't reflect the true population mean. But if I threw a coin a million times, I will get very close to the true population mean. Same with heights. I could go ask 4 women what their height is, or just measure them. Let's say those 4 women were 2 meters. Does that reflect the population mean? No, it could, but most likely no. But if I measured all the women in Norway, of course it will reflect the population mean. So this, the law of large numbers, makes a lot of sense. Okay, so what is also cool about this is that actually, when the sample mean gets very, very large, it actually, the distribution, and this applies for a lot of distributions, not absolutely all phenomena in nature, but a lot of distributions, is that actually that this random variable here will approach actually a normal distribution, which I'm not going to prove that because the proof is pretty crazy. I think it's not crazy, I just don't have the time to do it now, and I don't care, to be honest. I could just create some intuition, and this is the intuition. So for example, if I threw a coin or asked measured women, heights of women, if I threw a coin, right, the first data points, let's say this is the true mean. The first data points are going to be pretty random, right? They're going to be pretty random. But the more I ask, the more, because of the law of large numbers, the data points are going to be centered around the mean, right? So the more I ask, the more that is going to happen, right? So we get more and more points here, and more and more and more and more and more and more and more. And this, of course, is regardless of the distribution. Same, this looks like a third. But this is regardless of the distribution. Which means that they're normal, because the rarer event, they will create those nice tails, but the common events will create that bell shape in the middle. That's pretty nice. So this, you can see, is regardless. If I did height, the same thing will apply. If I did, for example, studied a Poisson distribution, where we had something like radioactive decay, that radioactive decay, most of the events will appear here in the middle, which create this nice bell, but the rare events will create the tails, right? So we'll get a normal distribution. Perfect. Okay, so that's the central limit theorem, right? So now we know actually that if we take some sampling of some data points, we actually can get the normal distribution, and normal distribution is very nice to work with. Okay, now we have all the tools to study the velocity of gas particles, because that is what we want. The next thing here now, so now actually starting to look at the thing, we have to have some assumptions. And the first assumption is the ideal gas approximation. Ideal gas means just that they don't have any extensions, which means that if I have some container like this, my particles are point-like. They are not extended or anything. They're just, we just assume them to be point-like. Also, as well, we have that the particles here, they have elastic collisions, meaning that when they hit each other, the kinetic energy isn't lost in the process. So it's just a pure collision where no energy is lost there. So that's just an elastic collision. And this is actually, for our case, a pretty, even though that's not how gases behave, but it actually works pretty well in our case. It states in my book that this is true when temperature and pressure is not extremely high or low. I found some opposite evidence, and what do they mean by extremely high or low? I don't know, but I haven't had chemistry, so that's all right. I just know that this ideal gas approximation actually work in our case. That's it. Okay, so we need a distribution of those particles. And the distribution we're going to use is the Maxwell-Boltzmann distribution, which for some reason is going to be pretty complicated. So we are going to deduce this distribution later in the course. But what I can do is create some intuition. So let's say you have some container like this. Let's say it's air molecules, like nitrogen, for example. So our air is mostly nitrogen, so we could just say nitrogen then. Okay? So we have these particles here, right? Or molecules, of course. And they have velocities, right? Like this. This guy have a pretty big velocity, and this guy as well. Now, if I measured the temperature here, let's say I got, for example, 300 Kelvin. Actually, the temperature, it reflects. We think of temperature as cold or warm, but temperature actually reflects the average kinetic energy, right? It's pretty easy to think about. If I took my hands, and my hands is the system, and I rubbed it, you can feel the heat, right? If I have some container with boiling water, when the container gets hot because the particles are slamming hard against each other and the container. They're heating up the system by the collisions, right? That's why temperature reflects the average kinetic energy. And as well, if I had this guy, and of course I could have, let's say I had the same container here. Now, with the same amount of particles, I don't remember how many particles there are, and I don't care either. This is just an example. So I have the same amount of particles, but they have less. This one has a big one, but on average, they have less kinetic energy. So let's say this was 200 Kelvin, like that. Then I could create a distribution where I measured the number of particles, so I have number of molecules, against the speed here, or velocity. We are going to use the vector form, but I could just say speed. It's all right. Then you would see that the first distribution, this one with 300 Kelvin, let's have this in blue. So this is the one with 300 Kelvin, would look like this. And the distribution with 200 Kelvin would look something like this. I could actually get even steeper. Like that. Makes sense. Now, why is that? These look also pretty normal to me. That's also what we want, because we want Gaussian distributions. And the reason why this is the case is that these two has to reflect each other, because we need the same total number of molecules. So the area has to be the same. If we have generally lower speeds, they are of course going to be centered around and taller, right? Because we have more of them, right? Since we have more of them and less speed, this one has to be taller in order to match this curve over here, right? Okay. That is just that. That is the Maxwell-Boltzmann distribution. Just a simple way of thinking about it. Okay. Okay. Now I've been given the equation. I've written it here. At least I'm not supposed to go and remember it. So the equation is P, and it's a function P of V is equal to M. Then we have M, and we divide M by 2 pi k t, like that. Then we have 3, 2, and then we have e to the minus, and then we have mv squared, like that, and then we divide that by 2k and t, like that. That should be all right. So it's minus this whole thing, and v is only one where that's squared, right? So what this says is that if this gives us the probability that a gas particle with a certain temperature and mass has this velocity here. Of course, this should be a vector as well. And k here is just a Boltzmann constant, right? Okay? Now we can, because this one is starting to look like the formula for normal distribution, but we can take it a bit further. Okay, we can state that sigma is equal to kt divided by m and the square root of that. And you can see pretty easily now, if I square that guy, what happens is that when I substitute for m will go away, k will go away, t will go away, m, k, and t, like that. And we can rewrite the expression as p of v is equal to 1 over 2 pi. Remember, I squared sigma, so I have squared there. 3 over 2 e to the minus, and then just to make things clear, we can just say 1 to sigma squared. And then we'll have v1 squared, vx squared plus vy squared and vz squared. Remember that, of course, if we had 2ab and this was v of x and v of y, they are in their perpendicular and will cancel. So that's why we don't need that. Okay. And we can do this even further. I can write this as 1 over, and I want the square root of 2 pi sigma, and I want to multiply it by e to the minus 1 over 2 sigma squared. Remember this with these. Remember, for exponential, when we have additions in the exponent, is it in the exponent? Is this in the exponent? I don't remember that word. When we have at least addition here, that's just, of course, multiplication. So we can substitute here, and this is just vx squared, and then we can multiply by the same thing. Then I have 2 pi sigma e to the minus 1 2 squared vy squared. Then I can multiply again. That's just 2 pi square of that guy sigma e to the minus 1 over 2 sigma squared and v of z, squared. And this is actually the formula for a normal distribution. So we actually have the probability here. This is equal to the probability in the x direction, right? Maybe I should do, in the x direction, p of x, and this is probability in the y direction, y, and probability in the z direction for z. So pretty cool. And all of this should make sense, because here, actually, you have what you have here, and you will have you will actually have this guy minus mu, and since mu isn't there, it's actually 0. So the population, or you could, that wouldn't be, it depends how to do it. I could say the population mean, or would I say just the mean itself? It depends, yeah. Let's just keep it as the population mean, or I'll just say the mean. So the mean here is 0 then, right? That makes sense because a particle can move in the x direction, and it can also move in the negative x direction, right? And that should average out. The particle itself, in terms of coordinates, doesn't favor +2 in the x direction or -2 in the x direction. It doesn't favor none of them. So, of course, it should be 0. So that's correct. All of these three directions are independent. That's also true. If I move in the x direction, that shouldn't affect me moving in the y or moving in the z direction, right? So these events are independent as well. And the standard deviation are the same, because the standard deviation is just the one we used here. And that's also true, because again, we don't favor any direction. If we don't favor any direction, of course, the standard deviation should be the same. So that is the conclusion that we have here for now. I think that was all it. Waste distribution equal in all direction. They all have the same. Yeah. So that's it. I will continue on that the next day. I just did one task. I messed a bit around with Python, so let's see how I did that. Let's see. Yeah, this exercise. So exercise 1A, you should read this section, blah, blah, blah. That's not important. We will look at some temperature statistics. In order to make it easy, we will focus on a tropical country where the mean temperature is basically constant all year. The mean temperature average over day and night in Kuala Lumpur is about 29 degrees all year. Assume that the fluctuations of the temperature from day to day is Gaussian distributed with a standard deviation of 2. Okay, first, calculate the probability that the mean temperature in Kuala Lumpur tomorrow is about 30 degrees. And it says prepare your favorite numerical integration algorithm. So I'm just going to use Python. It's assumed that we are going to use Python. So here it is. I just wrote down the CDF. It was just, I tried to import it from SciPy, so it just got weird because, yeah, I want to do it in light of the task. I just wanted to do it like, I think they want us to do it like this, and this is good learning too. So this is the formula for a normal distribution here. I also have the correct mean and standard deviation. Then I have a helper function, which I created, integrate. So it's just using some NumPy stuff to integrate. You have a start and a stop and a step size. So the integration bounds, and of course the step, which will be our delta x between the start and stop, of course. And we have f. Then I just use numpy.arrange to create this range here. So if I go from 1 to 10, I can have a step of 1. That will be like I go from 1 to 10 and 1, 1, 1, 1, for example. That could be my arrays of x. And I just sum up the step sizes, all the step sizes. That's what's so nice about NumPy, and the function itself. And the function itself is just a cumulative function, right? So that's integrate. Okay, so I just do integrate here. P is equal to integrate of this guy. I pass in the CDF here because that's our function that we're going to multiply with. And I print P, and if I do that, you can see I get this number here, and that's entirely correct. So that's it. That's enough for today. Okay, see you tomorrow.